of this season. Yeah, well, not least, of course, and not the last forever. Yeah, grand finale with Soonwon Choi. So we are late. I will make a short introduction to Soonwon. The fact there is an echo. So he's visiting us for a couple of days, and he's already packed. Like every single time slots is packed. I think that means that he doesn't need introduction. You can. The good thing about Sunwon is that there are like different aspects that every person would be interested to find that aspect, like Rydberg, unitary random matrix, quantum computation, whatever, sensing. So whatever you have seen in quantum information sciences, he has touched in a very beautiful way. So we are very happy that you accepted to come and also delay it for my sake. He got his PhD at Harvard, working with Michel Lukin. Then he went to do a postdoc fellowship at Berkeley. He did very nice works on random unitary circuits. And then now he's an assistant professor, right, at MIT. So with that, thank you very much.
Great, thank you so much.
You can hold it like a rock star, or
yeah,
you can put it like a speaker.
Can you hear me well? Okay, good. Thank you so much for a nice introduction. Thank you everyone for coming to my talk. So without further delay, let's just jump into the talk. Today, I'm going to talk about quantum computing enhanced sensing. And this work was done with multiple collaborators. Richard Allen is my student. Francisco Machado is an I-10 fellow postdoc. And then we also work together with Ai Chuang and Robert Huang. Before starting, let me just make one comment. This is the second time giving basically this talk. And this talk is going to be based on the work that's not published yet. We are wrapping up very rapidly, polishing the manuscript. So hopefully we'll be able to post it within a very short time, like this week or maybe next week, at least by the end of the this year. Okay. So for the audience here, maybe we don't have to explain why it's such an exciting time for quantum information science. In this slide, I presented three figures from three representative figures from three works that I particularly like. One is from Continuum. They demonstrated very high fidelity operations for the quantum systems. The second one from Michel Lukin's group, where they moved atoms and then demonstrated to a certain degree a logical quantum circuit. And the third one is a figure from Manuel Engel's group from Caltech, where they trapped successfully to 6,000 atoms. They have not demonstrated entangled engaged on these systems yet. However, they demonstrated the single particle operations maintains the degree of control and fidelity we can do. The reason I select those three is because each represents the quality of the quantum system we can achieve. Second one is a degree of control and the manipulation we can do. And the third one is the size. So combined all together, it looks very promising that we are going to have large-scale, highly sophisticated quantum devices. Okay, the key question is then, what should we do with these quantum devices? Maybe almost everyone in this audience might have thought about this question, what should we do? It's a very important open problem. And in today's talk, I'm going to argue that quantum sensing and metrology would be one of the most exciting and interesting directions to pursue. Because, in fact, in the history, it has been the driving force for new sciences and technology. To name a few, in 2016, we have detected for the first time the gravitational wave using highly sensitive quantum interferometer. This year, there was a breakthrough of building a better quantum clock, atomic clocks, or maybe in the future, nuclear clock. And maybe not yet, but maybe in the future, we will be able to detect dark matter or dark energy, maybe using advanced quantum sensing protocols, and that'll open up totally new avenue to area of physics that we can explore altogether. What's interesting is, even though they are on a totally different directions of physical science and technologies, in fact, the working principles are very similar. So let me just briefly recap quantum sensing. Everything can be understood basically around the spectroscopy. So here, let's imagine we want to detect a magnetic field strength B that coupled to a single qubit or spin-1/2 particles along z direction. What we do is we initialize qubit in a superposition state, which in the black sphere is represented the pointing along x direction, evolve under Hamiltonian for time t, they evolve by an angle v times t, and then rotate the basis, followed by performing measurement of up and down 0 and 1. And this population information encodes the theta and in turn our b value. So we can detect this signal b, we can tell whether it's 0 or not, as long as b times t is order 1 number. In other words, given total evolution time t, the strength, minimum strength we can detect scales roughly as 1/t. And this idea can be generalized for the multi-particle case. If you have a 1 particle, the minimum strength we can detect is 1/t. If you have n particles, we can just repeat the experiment in parallel for all n particles separately. Then just statistical averaging gives you square root of n enhancement. So 1/square root of n times t. We could entangle and then repeat m times the same protocol over time. And then the sensitivity is given as square root of m further enhanced, just repeating. Of course, repeating it takes more time. And this limit is often goes by name of standard quantum limit. But if you now entangle those particles, what happens is all this collection of n particles behaves one gigantic spin 1/2 two-level system with enhanced coupling strength by a factor of n. In that case, we can achieve scaling, that's 1/square root of n times nt. So relatively, we have a square root of n enhancement. And there has been many efforts to achieve this Heisenberg limit. How, for example, can we make this Heisenberg limit scaling more robust in the presence of error? Or maybe we design the sensors so that rather than using a GHZ state, more sophisticated state that has a better metrological gain. And this is closely connected to quantum algorithms or Hamiltonian learning. And there are many more approaches to basically achieve this particular fundamental limit. Okay, I already see many of the audience like yawning and like being falling asleep. Maybe it's very boring. So let me just stop talking about this. I'm not going to talk about any of this in today's talk. So sorry for wasting your 5 minutes. Instead, I'm going to ask fundamentally different questions. Metrological enhancement, they are qualitatively different from all the examples that we mentioned so far. And I wanted to just explain what is the overall thinking or the perspective that we've been thinking about on the metrology, because I want to go away from it. So specifically, in this talk, let me emphasize that all the kind of approaches we've been discussing so far is on the following paradigm. So we have a conventional settings where they have an entangled set of particles. We have computers that applies maybe light or electromagnetic waves, the microwaves and so on. Maybe utilize interaction among them and entangle them and try to detect sensors. But for today's talk, let's be futuristic. Let's assume we have a fully functioning quantum computer. For now, let's assume it's a fully corrected, error-corrected scalable quantum computer, just to simplify our life. And then that can be entangled, and they can control the entangled sensor particles. And the question is, can we leverage quantum computational advantage as a way to improve our quantum sensing technique? And that's going to be today's talk. With that point in mind, this is like my outline. I'll first talk about a particular task where we can show there's enough evidence or like proof that a certain task for which we know the quantum computing can be very useful. And then we'll present an optimal algorithm that performs that task. I say optimum because we have both the fundamental limit that we show cannot be cannot be surpassed, and then we saturate the limit by our algorithm up to logarithmic corrections. And then we'll have some general discussion about what it means by computational enhanced metrology, and then talk about how to implement our proposals as for the proof of principle in the near-term experiment. And I'll present a certain, the pulse level, the implementations, and then talk about summary, discussion, and outlook. So the task we are going to talk about is the following. Suppose we are tasked to determine whether there exists a very weak oscillating field, say B of T. And then B has a strength B, cosine omega T plus phi, and that's coupled to my single qubit as Z. We could consider n particles, but now let's assume that the n particle is always in the GHG state, assuming so they effectively act as a single particle. So most of the analysis will be basically single particle picture. Okay, and the strength B is unknown and very weak, very small, and it sets the sensitivity, and the frequency omega is also unknown. However, we assume this frequency is within a very broad interval, delta omega, and then phase is also unknown value. So our goal is to tell whether there exists a signal or not at a relatively short time, as quickly as possible. If you can achieve this task, what we can do is we can do this task for different frequency intervals and then nail down each frequency value. And once we know the frequency value, we use a conventional sensing approach to precisely measure the strength of B. Therefore, this approach, like telling the binary alpha hypothesis test problem, is a basic building block of doing this particular AC sensing task. So let me call this the broadband AC sensing. And broadband AC sensing is characterized by two numbers. One is minimum strength that we can detect, B min. The other one is the size of the frequency window under consideration, bandwidth. Yes?
So, will this also detect two signals at two different frequencies? Like, is this like a question of like, is there any signal in this window?
Yeah, in these settings, we consider is there any signal in the window or nothing. Imagine I want to measure like Xion field or the dark matter field, candidate field. I don't know the frequency other than some range. Let's assume for now there's only one coherent field, and the strength is very weak. But let's assume it's larger than a certain minimum value, because otherwise it'll, if it's infinitely small, of course it'll take infinite time. Yeah.
Is there an assumption built in somewhere in the protocol that there is only, if there is a field, there's only one field with one frequency? Like if there are two frequencies, will that throw you off somehow, or will that be?
Yeah. So we formulate task as a one signal at one monotonic frequency. Our algorithm will still work, even if there are multiple tones. Yes.
I just want to see the metrics that you're using for assessing how well the protocol performs. I was wondering about the upper right-hand side of the slide, that as quickly as possible. Is the time needed to perform the sensing another metric that you're interested in?
That's right. That's the only metric I'm using, like the time needed to detect these signals, sensing time. What other metric can we imagine?
Items at the bottom were supposed to be the metrics, like the sensitivity is a metric by which we assess the quality of.
Oh, I see. Okay, so we have three important parameters. Time that we need to run our lab, experiment. The other one is the sensitivity that we can achieve, and the bandwidth we can achieve. So our figure of merit could be fixing two and the other one, like what is a minimum that? For example, given total evolution time, the total sensing time, and the bandwidth, what is the minimum sensitivity? Or given the sensitivity and the bandwidth, what is the shortest time it takes, and so on. Okay, so it's an interplay of the three parameters. That's right. So in here, we'll fix the two on the bottom and then minimize the total time. Okay. Any other questions? Okay. And this sensing problem is practically useful one. Obviously, has a close connection to gravitational wave detection or dark matter detection for NMR experiments, and also indirectly like design of quantum clock. And this broadband AC sensing is also conceptually important problem from a pure theory levels, because we can consider this as a simplest possible instance of time-dependent Hamiltonian learning, where there has been a lot of work in Hamiltonian learning work, but most of them were time-independent. And for this time-dependent Hamiltonian learning, formal hardness, okay, what if the complexity, sample complexity, or like query complexity, or the optimal algorithm has not been understood very well. Specifically, as we just talked about, the figure of merit that we are going to use is total sensing time. What is the total duration of the time that I need to evolve under the given unknown Hamiltonian? And usually the minimum time will be depending on the algorithm, but also it will be a function of the target sensitivity B mean and the bandwidth delta omega. And let's talk about the conventional approaches to solve this AC sense problem. In the conventional approach, which actually happening today on a daily basis because we are actively looking after detecting dark matter, the approach is basically the following. Given total bandwidth delta omega, we are going to divide them into the smaller bins so that there's m frequency bins. And then we are going to target a particular frequency window and detect the signal and tell whether they exist or not using the state-of-the-art, perhaps like Heisenberg limited sensing protocol. Okay, that's the state-of-the-art. And if you detect the signal, then we get Nobel Prize. And if you don't detect the signal, we go to the next bin and then detect. If you scan over the entire bin and don't detect it and then publish a paper, okay, we just nullify this area and there's no signal. Therefore, the theory needs to be modified. So that's the kind of very simplified, the picture of what's happening in the community. So how do we detect the AC signal in the in a conventional way? Say there's a signal that exists at a particular frequency. We do exactly the same as Ramsey. We initialize along x, evolve under time, and you pick up a phase, theta. And this theta is going to be integral of the B field. The problem is B field is oscillating over time. So if you integrate, they'll be basically 0. So we won't be able to detect AC field. So if you want to detect AC field, we do something slightly different from Ramsey, where we just apply pi pulse at a certain time interval, space by time interval, TP, pi over omega. Okay. What happens is, if you move into the toggling frame, or like if you just flip the operators instead of operators, then this applying repeated pi pulse amounts to flipping the sign of the signal. So this oscillatory signal now becomes on average finite value. So due to this pi pulse, if you integrate over theta with applying this so-called filter function or the modulation function ft, then we accumulate the signal again. Finally, the same as Ramsey, we just rotate to the z basis and perform measurements. Okay. So in this way, we achieve the sensitivity just like before, 1/t. And the bandwidth will be determined by what is the window where this oscillating signal still get rectified to time constant signals. And that's related to the Fourier limit of our modulation function. So it will be 1/t. As long as frequency is near the target frequency with the window less than 1/t, then it will behave like quasi-static signals. So the bandwidth of this particular iteration will be 1/t. Therefore, if you do the sequential search using our conventional search, here is the time scale. So each bin sensing, let's say takes time total t, a large t. Sensitivity is 1/t. The frequency bin size is 1/t because that's the bandwidth of each AC sensing. Number of intervals you need to introduce is the ratio of total, bandwidth and the small bandwidth for each iteration. That's m. So combined together, the total conventional sensing time is going to be t times number of intervals, which is just like nice number, delta over delta omega over b mean square. Turns out this scaling, as we will show and discuss more, it's quite universal. Any sequential search will be like this. Turns out any approach based on quantum efficient information will be this. It doesn't matter what value of large t we choose, it will be the same answer. It doesn't matter whether you divide into sub-ensembles or divide and conquer for the n particles. So it'll basically all have the same scaling. So there's a total sensing time. So the conventional approach, the sequential approach, have a total sensing time that scales as 1/b min times delta over b min. I intentionally rewrote in this way because first factor 1/b min is basically the iteration of one unit. The second one is a number of bins they need to scan. Plotted in this way, we can get more insight. So y-axis is the sensitivity, and the axis is the bandwidth, plotting the logarithmic scale. If you have n particles unentangled, we have this orange line where everything to the top left is achievable, but there's a fundamental line set by the total evolution time. Given total sensing time, we cannot go below this line. So we see there's a trade-off between the sensitivity and the bandwidth. If we give up the sensitivity, we can increase the bandwidth and then follow those lines. Now, if you entangle those particles together, we have a square root of n enhancement going downward. So the Heisenberg limit is a yellow line. And there we have this curve shifted down because we have a collective enhancement. The question is, can we do better than this using quantum computing enhanced sensing? So let me just tell you the answer first. So our first result is to show we explicitly construct a quantum algorithm such that we solve this problem with n sensing particles within time scaling like this. The factor of n is in front of b min purely because we have a GHG state. Effective coupling is n times larger. At the same time, the second factor compared to the conventional case, in the bottom, we have a square root. So in the limit of large bandwidth, we have a scaling improvement for the quantum search sensing task. Any questions here? Okay. So this big O tilde means that it's up to logarithmic factor. Yep.
Can you formulate kind of a bit more rigorously, like what problem are you actually solving? So I mean, in the previous slide, you showed this a two-level system driven by some magnetic field and then some additional signal. Like here, it's no longer just one spin, it's
That's right.
like a mathematical problem.
Yes, mathematical problem is distinguish Hamiltonian equals to B of t sum over j is zj, 1 through n. So n particles each coupled to z with a time dependent signal bt, or Hamiltonian equal to 0. We have ability to evolve under either of the Hamiltonian, and what is the total time needed in order to detect if it's a signal exists or not, distinguish those.
And you can apply anything you want to this particle.
That's right. I'm assuming I can introduce everything. I can introduce ancillary particle that's not coupled to the field as a quantum memory, and then apply entangling engage within the sensing particles, or within those particles, or my ancillary particles, or entanglement between the sensing particles and ancillary particles, and all the operations. And I assume the type of operation we can do is unlimited and arbitrarily fast.
Last question. So, I mean, if you're trying to detect the signal, well, I guess Z is just the physical direction of the field, or it's a metaphor for something else. I mean, how do you know it's going to be Z and not one thing?
So Z is just a operator from qubit. So I just meant to say any single qubit operator. So it just you can without loss of generality define that as a Z operator. Okay. Mathematic, if you really want mathematical, this is any operator with the operator norm equal to 1, less than or equal to 1. Yeah. Any other questions? Yes.
Just to check, we do know the direction of the field.
Yes, let's assume we know the direction of the field. Yeah, that's right. But that doesn't change the nature of the problem too much, because we can try x, y, z, and then it's 3 times, so factor of 3. Yeah. Good. Any other questions? Yeah.
So you explained that the coupling to the unknown field is linear.
That's right. So I'm assuming there's a coupling string G, and I set this G equal to 1.
Then when you assume that you can couple this to an ancilla, and then you can do things arbitrary fast. Does it mean that you're effectively coupling to that field with higher order operators?
No, we cannot. You cannot enhance, and physically we cannot enhance the coupling by bringing more particles, that's not coupled. We can reduce them, but we cannot amplify them. Any other questions? Okay. Good. The second result, I'll talk about the algorithm in detail, so let me just move on for now. The second one is optimality. So at the same time, we proved that, in fact, any algorithm, quantum algorithm, that involves arbitrary number of ancillas, arbitrary, game operations, arbitrarily good, arbitrarily fast classical computations, intermediate measurement followed by feedback. No matter what you do, the sensing time is lower bounded by basically the same scaling formula. From that sense, our algorithm is optimum. And for the reason that's pretty obvious to some people, we call this bound a Grover-Heisenberg bound, because essentially we have a Grover improvement on the bandwidth side in unit of Beamin, and the sensitivity scaling is the same as the Heisenberg limit. So putting these results all together with our previous phase diagram, we have this new landscape: sensitivity, bandwidth. So when we give up the bandwidth, when focus on the sensitivity, we should look at the terminal point of this line on the bottom to the left. Our Grover-Heisenberg limit does not improve beyond Heisenberg limit for a fixed sensitivity, fixed bandwidth or narrow bandwidth. But if you have to consider the broad bandwidth AC sensing, we have a different scaling formula so that we can improve better. Okay. So the question, yeah.
For a fixed time tau, right?
That's right. That's right.
Fixed tau, is that possible? How much can you remove the impossible?
Here we are talking about ideal regimes, assuming there's no finite coherence time. If you want to talk about finite T2 case, we still have partial improvements, and we can talk about that. But I have not prepared the slides for them. I'm happy to discuss. Yes. Yeah. Yeah. Any other questions? Yes. Okay. So let's talk about how we actually construct algorithms. So the idea is very simple. So we have an AC sensing problem, but let's translate them as a computational problem, and then solve quantum algorithm that solve the computational problem. In our case, we are going to interpret this whole sensing problem as a search problem for an obvious reason. So we have these different beams, and we first set the target sensitivity beam in, and then we try to find any beam that contains a signal whose strength is larger than the sensitivity target. And that's so-called a marked element. So there's a marked beam. And then if you find, OK, there's a signal. But if you cannot find, then OK, maybe there's no signal. Or maybe we should set the sensitivity parameter lower and then repeat. So from this sense, this solves the sensing problem as well. In fact, this is slightly stronger because we not only tell whether a signal exists or not, but we automatically tell which beam contains a signal. Therefore, we learn about the frequency simultaneously. So it's slightly stronger. And then to find this beam, we are going to use well-known Grover search algorithms. So Grover search algorithm, everyone knows. So let's go very quick. Suppose we have a very large number of entries in the database. Here, I make analogy to the books. And we want to find a specially marked one. But in order to check whether the book is marked or not, we need to open a certain page and then check whether there's a mark or not. And this check process is going to be very important. And in the classical computer, there's no information about marked element unless you have to check it every time. So on average, we need to take open the check n minus n over 2 attempts. But remarkably, in the quantum algorithm, we can accomplish this task with the probability 1, only checking square root of n attempts. The check operations. And this is an example of provable quantum advantage without any assumptions that leads to quadratic speedup. And we'll come back to many words here. So the idea is, conventionally, we had different beams, and the number of beams is delta omega over n b mean. And we have a square root of enhancement by applying the Grover algorithm. So it's going to be Grover speedup. I could just complete my talk here, but that would be very boring. In fact, one of the Grover's very original paper mentions detection of quark because they thought about using Grover's algorithm for such a physicsy problem. Turns out the sentence they wrote is in a negative side. In reality, we won't be able to do that for the several challenges that I'm going to discuss. So in fact, this Grover speed up is a very naive approach if you just think about it, because we need to assume there exists Grover oracle. The oracle is a formalized version of check operation. We check whether there's a marked element or not. So in the formulation of Grover's algorithm, we assume following oracle, access to the following oracle. So we have a superposition of all different K enumerating different books, and there's an output registry like 0. After running the oracles, only from the marked element, we flip this auxiliary qubit, telling that, OK, this is a check operation. We should be able to do this operation unitarily in a coherent way, maintaining the superposition and even the entanglement with the rest of the systems. And this access to the quickly verified marked element while maintaining the coherent superposition is one of the assumptions that Grover's algorithm makes. In the sensing context, this should be formulated in the following way. We have quantum computer that enumerates, maybe in a superposition, different K. So it has a different frequency beams enumerating. And then we have a sensors connected to the quantum computer, but maybe in GHZ state. And then we have an extra ancillary qubit 0 to write down the query output. such a way that once we evolve under this unitary circuit, only for k that contains a signal, you flip the ancillary bit. But otherwise, it does not change. So we need to have this Grover oracle to build sensing. However, it's challenging because first we need to accomplish this unitarily and way that's compatible with the coherent superposition input X. And sensors must be decoupled, and so that we can reuse the sensing state, the sensor state after several iterations of Grover's oracles. And also it has to be done in a high fidelity because in order to achieve scaling regimes, we need to make sure many iterations of this does not affect the fidelity. And there are more challenges. We assume the signal strength B is time dependent with unknown value of B. Even if B is larger than B min, we don't know its precise value of this. And also our frequency omega may be inside a particular bin, but within the bin, we don't know where it is. And closely related, we don't know the sensing phase. And more interestingly, every time we interrogate nature, because we don't know the frequency, effective phase we access is different. Therefore, we should not assume this coring the sensing as if we are doing the regular oracle settings, because in some sense, we don't know what's going on in the oracle that we are utilizing. So in short, what we want to do is we want to map all this analog coupling signal to a discrete Grover operations. So you change the value of strength B or phi or omega within some relevant parameter regimes, the output should not change, even though it's unitarily implemented. And that's the challenge. And this idea is what I call as a digitization. We need to perform unitarily a transformation of analog signals into high fidelity, high accuracy, discrete gate operation. And that's going to be a technical challenge that's needed. And that's one of the reasons why, even in this Grover's original paper, implementing Grover's algorithm for real world physics could be very challenging. So I'm not going to get into the details of every single details of our algorithm, but I'll just briefly mention 3 key ideas and only focus on one, namely the middle one, to illustrate what type of physics we are utilizing. The first key idea is coherent superposition sensing. So recall the conventional AC sensing is done by repeatedly applying the pi pulse. If you do this, depending on the timing of the pulse duration, we are selective, we are sensitive, only selective to a particular frequency that happen to be resonant to the pulse spacing. And we can immediately generalize this for the quantum computing settings. So instead of applying pi pulses, which is X gate, we apply controlled X gate. So quantum computer is in a state K, and only when K is a certain value, you apply controlled pi at a certain rate, so that the spacing depends on the K. In this way, we can implement the different sensing in parallel, where the pro frequency is tuned by our register state of the qubit. So achieving this coherent superposition sensing is not terribly difficult if you do this, if you stick to this approach. However, this approach is slightly problematic for different reasons, the following reasons. So here, when I explain this pi percentage signal, I intentionally drew a simplified and an ideal case where the signal and the duration of the pulse are perfectly synchronized. But who knows? Maybe this phase is accidentally different from what I expected. So instead of accumulating positive signal, maybe accumulate the negative signals. So instead of accumulating positive direction, you go to negative directions. In the classical sensing case, it's okay, because if you perform measurement in the right basis, either case we can change the measurement, the directions. But in the quantum case, that means our oracle construction will be unreliable, because depending on the phase, the oracle does different operations. So what we want to achieve is, no matter what the phase of the signal is, we want to rotate the qubit in the same direction without compromising the sensitivity scaling. And that's going to be the challenge. And I'm going to explain how we overcome this challenge a little more detail in the next couple minutes. Okay. So the key idea is this. So one insight is we understand this type of sensing scheme as a version of Hamiltonian engineering. For example, if you do the right, perfectly matched these protocols, we convert this AC signal into the DC signal, and that amounts to the transformation of a Hamiltonian. You can understand this basically as a dynamical decoupling, where time-dependent signal has a shifted frequency, delta K. The delta K is a detuning, we're detuning delta k is the difference between the actual frequency omega and the target frequency, where it's set by the interpole spacing. And once you do the Hamiltonian engineering for a specific choice of omega k, when delta is sufficiently small, the signal becomes quasi-static Hamiltonian that rotates qubit along z. That's why we could use a Ramsey. For our purpose, we are not going to do this, but going to do something similar. So what we do is this. We are going to engineer such a way that the effective Hamiltonian we see is in general tilted. And in tilted such a way that the direction along the xy plane is proportional to the signal strength b. And furthermore, we have this chi-t factor that's all at most 1. We have ability to tune down and actually kill the interaction. It turns out killing the interaction is useful in order to achieve the high fidelity. So we assume we have a tunability of signal from 0 to the maximum size, which is b. And if it exists, it will be always in the xy plane. However, within the xy plane, we don't know exactly what angle it is, and that angle is going to be the phase of the signal. We can engineer this Hamiltonian. And then the z direction field will be determined by the frequency difference, delta k. And delta k is the same delta k as before. So specifically, the Hamiltonian we are going to engineer is written in the board. And what's nice about this Hamiltonian is that the energy eigenvalue, instantaneous energy eigenvalue of the Hamiltonian does not depend on phi, because it only depends on the total strength of the field, but not the phase in the xy plane. Therefore, what we are going to do is not the quench dynamics, but adiabatic evolution. So I'm not going to like the every single details, but what we do is this. We start from chi equal to 0 and delta to be very large, so that the field is basically z direction, and we start from that eigenstate. And then we change this chi and increase to its maximum value, and that will adiabatically tilt the angles. And if it's done slow enough, then you will pick up dynamical phase, and then eventually bring it back. This way, we start from up and ends with up. However, you pick up the phase, dynamical phase, that encodes information about B. If you do this procedure too fast, then you will not come back to the original state, so it's problematic. In order to do the high fidelity, you need to do it slow. If you do it too slow, then it's not being optimum, because we are wasting too much time in order to achieve certain sensitivity. In fact, if you go into the perturbative regimes, then you will reduce the maximum sensitivity we can achieve, because it will be quadratic in general about the strength of the B. But turns out we can use idea called the supra-adiabaticity. The idea is, as long as this path is not adiabatically slow, but reasonably slow, then assuming this path is smooth enough guarantees that you come back to the original state to near perfect fidelity while achieving the dynamical phase in a non-perturbative regimes. And for that, we had to rely on the adiabatic quantum computing literature. So here's a very short technical slide about how to engineer this Hamiltonian. So let me just, unless you are interested, I'll just go fast. We basically dynamical decoupling and the basis change, add extra z field and the rotating frame and rotating wave approximations, and then we can achieve the Hamiltonian. So if you'd like, take a pictures, but otherwise, let me just go on. Okay, Alexei is taking the picture. Good. Okay, thank you. Okay, good. The third is this. So far, we implemented a way to do the coherent superposition sensing and phase agnostic sensing. But now the problem is like final step of digitizing it. So conventionally, we focus on designing our approach, whatever it is, so that the response to the signal is as sensitive. So we want to maximize the slope. But what we want in this context, in our problem, is behavior like this. There's a threshold B min. So whenever B is larger than the B min, it's like 1 or like some value. Otherwise, it's basically near 0. So we want to this nonlinear response. And in fact, in the past few years, there's a remarkable development of engineering this nonlinear behavior called quantum signal processing. So for some algorithm-based people, this is be obvious, but for maybe experimentalists or some AMO people, this is how it works. It's basically a complicated and advanced version of composite pulse. Imagine we have rotation along x, z, x, z, x is alternating for depth p. Each time apply rotation along x, you rotate by some angle that we can tune, we can choose. And they can be different in each iteration. Each time we rotate along z, we rotate by the same angle theta, but it's unknown. Turns out these alternations applied to a single qubit will be some 2x2 matrix, but that 2x2 matrix will turns out to be the rotation along z, but the amount of the rotation angle is a nonlinear transformation of theta. And the transformation function f of theta is determined by the choice of this control angle phi0 to phi l. And there's a systematic way of engineering a particular f by a certain choice of phis. And we are going to use that. We are going to choose a smart form, polynomial functions, such a way that this function f approximates this step function. That's what we do. Okay, so combined together, we have the following situations. We start from an analog response as a function of strength, B, and the function of phase. Conventional sensing has undigitized approach, accumulate the phase that varies differently. But in our approach, this is a schematic, it's not a numerics. Like here we have a digitized approach when there's a threshold behavior for B and the near flat behavior of theta. So let's talk about how much gain we can obtain by using these Grover algorithms. So this is like basically the algorithm part. So any questions so far? Okay, otherwise, yeah.
So are the pulses, are they gone, or you're still doing 5 pulses?
The pi pulses are basically gone, but the pi pulses are hidden because when I engineer this Hamiltonian, there's a dynamical decoupling involved, and also so basically, if you see here, we add a z term, z energy shift. Basically, we make the transition frequency to be resonant to the particular frequency depending on the answer law. So that's what it's done. It's kind of done in an analog way. Okay. Yeah.
So I think one important part of this algorithm is how to construct this oracle very efficiently.
That's right.
I wonder whether this is specific for this kind of sensing type or it's very general, maybe for even more general.
Oh, yeah, I'll come back to that. Yeah. Okay. Yeah, that's right. Any other question? If not, please remind me. Okay. Any other questions? Okay. So now let's move on to how much gain we get. Like I already said, we have Grover speed up, like quadratic speed up, right? So naively say Grover managed quantum the quadratic speed up. Who cares? It's only polynomial. It's not exponential. So people are turned down. Well, that's not the case because we have to be more careful. The computation time and the sensing time, physical sensing time, are different because usually when we talk about computation time, we talk about query complex, how many accesses we need to do. But here we don't care about the number of times we need to access this, the total duration of the time we access this. So as already have seen, we have a parameter, like 2 different parameters, sensitivity and the bandwidth. And depending on which regime we go, we have a different amount of metrological gain. For example, if our target sensitivity is so large, or the bandwidth is so small, the small bandwidth regime here, our approach will not improve more than Heisenberg limit. That's a fundamental limit. So it's not useful for the narrow bandwidth sensing. However, if you have broad bandwidth sensing with the larger Bmin, so go up to the right, then the separation between the Heisenberg limit and the Grover-Heisenberg limit will be larger. In fact, if you assume a structured systems, for example, let's assume the coupling strength here, the coupling strength between the signal and the field is actually depending on the frequency, as is a case for example, the stereo theory for the detection of axions. And if you assume the dependency is say omega to the mu, for the range of mu between these two values, we have a bigger separations where quantumly we can detect the whole frequency range within order 1 time. But classically, it takes time that depends on the bandwidth of the signal. So we can achieve bigger separations if you have a more structured systems. And by the way, the believed coupling mu, I'm not an expert, but for the axion is I think 1, but I'm not an expert, so don't call me on this. Okay. So the original metrological gain. So conventionally, we understand where the enhancement sensitivity, the sensitivity enhancement comes. That's coming from the collective behavior. And particles behave as one particle with the enhanced coupling. But in the quantum search sensing, well, we argue it's coming from the computational origin, but rigorously pointing out is very difficult. In fact, even though I presented as if these are quantum sensing particles controlled by quantum computers. Mathematically, there's no sharp boundary between sensors versus computers, because if the coherence time of the sensing particle is good enough, we can use a subset of them as a quantum computer. So mathematically, okay, pointing out, hey, here's a computation and here's sensing is not really well defined. So instead, we are going to approach slightly differently. We're going to figure out, okay, what are the key ingredients? What makes our approach qualitatively different? And that's distinguished from the conventional sensing. And that's I think that's more meaningful. I'm going to focus on that. And the first aspect is non-perturbative approach. It turns out this non-perturbative, non-linear approach is necessary. So usually, the sensing is done in the linear approach. Say we run some algorithm preparing the quantum state psi at time t psi of t. Usually, we design the protocol so that in the absence of the signal, we prepare psi 0. But in the presence of signal, very weak signal, the state is a little perturbed by some perpendicular direction psi perp with the effective coefficient like alpha times b. And turns out this alpha and the quantum Fisher information is related to one another. Okay, that's a typo. That's an upper bound. The quantum Fisher information is upper bounded by 4 times alpha square. And we want to maximize basically this alpha, amplitude of alpha. Makes sense because we want to deviate as much as from the original case. And in order to solve this AC sensing problem, we want to make sure that deviation is detectable with a few number of measurements for all frequencies. So we want to demand this alpha b square is order 1 for all frequency. And that translates to the fact that quantum Fisher information averaged over the interval should be sufficiently large. And we can prove that's not possible. In order to use this approach, any approach based on quantum Fisher informations, fundamentally, the sensing time that's needed scales in a conventional sequential sensing way. So this proves that, in fact, the quantum Fisher information is of limited use, and it does not actually characterize it. A corollary of this is that any optimum approach, as achieved by as in our algorithm, has to have asymptotically vanishing quantum Fisher information. Because our algorithm runs much shorter, you have no way to have finite average quantum Fisher information. So vanishing quantum Fisher information is a necessary condition for optimality. The other one, non-classical control is necessary. So for example, we can do the sensings in the somewhat arbitrary but restricted control. Say the amount of control we have is changing the strength of the field B effectively between -1 to 1. So we cannot increase it, but we can reshape it in whatever the form, time-dependent form. And it turns out many of the protocols, like called the CPMG protocol or many other conventional sensing protocols, falls into this case. And with these restricted settings, we can also prove that the quantum sensing has to take this conventional sensing bound. So we cannot go beyond by designing good filter functions, even with the entanglement. So in summary, we have a 3 ingredient: non-linear, non-perturbative approach, and non-classical control. And I didn't talk about it, but turns out like long coherence time is also needed. If you have a limited coherence time, then we cannot achieve the bound. So combined all together, we argue that coherent nonlinear quantum information processing is a necessary ingredient to achieve this optimality. So let's move to the experimental realizations. So I guess it's okay to spend 5 more minutes. Okay. So near-term experimental implementations. So far, I've been explaining quite abstractly, assuming arbitrary quantum computer or not. But turns out the actual implementation is going to be extremely simple. So what are the ingredients we need? We want to engineer some entangling gates so that we can do superposition sensings. And also Grover algorithm has these Grover reflection operators, and that's in general entangling. So we have a capability to do that. And also we need the sensing primitive for phase agnostic sensings and single qubit manipulations. Remarkably, quantum signal processing is done by just single qubit manipulation. So the algorithmic component turns out extremely small. And I'll argue actually this whole thing can be done if you have only 2 ingredients. One of them is single qubit rotations. So it's kind of free. We already have. The other one is central spin model with the Ising dispersive interactions with the Hamiltonian of the following form. So this is ZS is a Pauli Z of the sensing particles. And we have an Ising interaction between sensing particles with a number of quantum register particles, quantum computer particles with the varying strengths Ji. It would be nice if you tune Ji, but if you cannot tune Ji, still we can do something. So why? This Ising interaction can be rewritten in the following way, like this. So condition on the configuration of the computer, like computer qubit, we have a different transition frequency of the sensing particles. So the energy diagram of this whole system can be summarized in this way. So we think of it as the computer degrees of freedom as a binary bit strings. And for the different binary bit strings, we have basically the qubit with the transition frequency that depends on the configurations. We choose J such a way that none of these, the transition frequencies are perfectly degenerate. In fact, the generic choice will give you this kind of structure. And then what happens is, if there's a very weak oscillating signal that's tuned to one of the transitions, but off resonant to the others, only for that particular state, you will have a coherent transition from the 0 state to the 1 state. Okay. So if you want to do the full-blown implementations with the unknown strings B, we can use that as a primitive and then design a quantum signal processing. But let's talk about a more simplified case. Say we know if signal exists, it's going to be a particular value for now, just to simplify the protocol as a proof of principle. Then we can simply wait the right amount of time so that it completes a 2-pi pulse. And net effect is you haven't changed anything on the sensing qubits, but you picked up the -1 phase of that particular register configuration. And that's all we need for the superposition sensing. And at the same time, that's all we need for the Grover oracle. And turns out we can also implement Grover reflection operators by artificially applying weak signal, 2-pi signal, to a particular configuration 0, 0, 0. Okay. So this is the simplest idea. And this type of dispersive Ising interaction appears almost everywhere. So for example, a particle, they get atoms in the cavity due to the Ising interactions. Or like Rydberg atom array systems, or superconducting qubit systems, or superconductor coupled cavities. Basically, any quantum system, if you put them together due to second-order perturbation theory, only energy shift is going to be basically dispersive, unless you fine-tune to avoid that. So basically, the requirement is extremely mild. So we have done a little more careful, in-depth studies, like as a benchmark. Focusing on MV centers. So many of you know MV centers, so I'm going to skip. You can think of it as artificial atom trapped inside a diamond. But usually MV center is surrounded by other impurities, spin degrees of freedom, for example, the nuclear spin of nearby carbon-13 impurities. And they interact one another. And in fact, we can control MV center in order to also initialize this carbon-13 or rotate and perform manipulations. And they realize almost exactly the Hamiltonian we want. Depending on the carbon-13 configurations, the transition frequency of MV center changes. And using this, we can implement the pulse-level implementations of our algorithms, assuming a simplified case where the actually not equal to 0. Like if the signal exists, B is known to be a certain value, and then frequencies happen to be one of the transition frequency. So just for the not realistic case, but for the proof of principles. Then our algorithm, this whole Grover algorithm is basically this plot. So we involve basically a full pulse, repeated again and again. One pulse is not even pulse, it's like exposing to the signal for a certain time. So they do the 2-pi pulse. And then we have a Hadamard gauge on the C13s. In between, we have targeted 2-pi pulse at the frequency 0, and that implement the Grover reflection operators. So with this, we can actually implement our approach. And then numerical simulations based on the finite coherence time gives us the following. So we define the improvement factor as a ratio of what the time it takes if you do conventional approach versus our approach. So large improvement factor means our approach is good. And this improvement factor depends on the field strengths. And also different curves is for the different coherence time. So the higher curves is the good coherence time. If the coherence time of the whole system is very large, we have an increase in the improvement as B increases. It saturates due to the size of the ancilla we have. Like here we assume there are 8 C13 particles. Eventually come down because if the B strength is so large, we cannot resolve them in these 2-pi pulse due to power broadening. And this is a plot for how the improvement factor scales as a function of total number of C13. Because the number of ancilla and the number of beams we can probe is related by exponential factor, we can actually follow the exponential curve, exponential improvement, assuming sufficiently good coherence time. The state-of-the-art experiment actually achieved this yellow curve, so we do have non-zero the improvement. But in the future, if we improve our total coherence time, so these numbers are very optimistic, but not crazy. It's a realistic, optimistic. We can actually achieve, improvement all the way up to say factor 10. In general, if you do analysis in the presence of finite coherence time, our improvement factor goes as the strength of the signal times effective coherence time. I say effective because it's not a single particle coherence time, but shortened coherence time in case the sensing particles entangle one another, which usually shorten the coherence time. Okay, finally, I'll have like just 1 minute because I want to answer to your questions. So I want to bring up what we are doing here, in a bigger picture. Let's zoom out a little bit. So in computer science, there are many algorithms that set apart the classical computing power and the quantum computing power. And usually that goes by oracle separations. They rely on the assumption that we have access to a certain oracle. Here, Grover algorithm example of that. And we can achieve like rigorous version of the separations. Here, what's oracle? Even though we did a massage in engineering or Hamiltonian, essentially the oracle is a nature. So nature is given. Because we are doing the sensing problem, figuring out what the oracle is exactly the problem we want to ask. Therefore, literally oracle is given, God-given for us. So the question is how much generalization we can pursue along these directions. And we have shown that, in fact, any Boolean function can be encoded as a particular time-dependent signals. So if you give the signals, and then you do the sensing protocols, you can encode such a way the response to the signal encodes any arbitrary Boolean functions. It's extremely inefficient in terms of the constructions, but in principle, it's possible. So that could be a good starting point of building connection between quantum sensing and then Grover oracle. So the oracle separation. So maybe that's the question you wanted to ask. The second one is this idea of having robust interface between quantum sensor and quantum computers. So here, our approach is different from collecting information first and then performing quantum computations. We have to simultaneously data process and more advanced way from the sensors. Inevitably, we have a noisy like sensors directly coupled to the logical degrees of freedom of quantum computing, but there's a problem. The problem is sensors are by nature sensitively coupled to the environment, including unwanted noise. But usually in quantum computation, we want to perform a quantum matter corrections so that it does exactly what I want to do without any unknown parameters. And this gap is an important problem that we need to resolve. Okay, how to coherently couple noisy sensor degrees of freedom with the logical quantum degrees of freedom in a controlled way, and what is the theoretical limit of accomplishing that. So that's the last slide, and let me finish with this one slide. Thank you so much.
Have the usual 4 p.m. speaker.
So, like this last explanation, the simplified protocol, it seemed like very intuitive, right? So you design, I guess, the qubit sort of computer Hamiltonian such that there are transitions at all of these frequencies, and then it kind of does one of the transitions, and you know what the frequency is. Like it's super simple.
Yes, sir.
So why was this like all this complicated discussion before that? Like with this quantum signal processing, like is some of that just not necessary, or is it all included?
No, that's very necessary. The simplified protocol is like 2 pi pairs. In order to find out 2 pi pairs, we need to know the value of the candidate signal. In the realistic settings, that's not the case because you don't know the value. So it boils down to the idea of how do you implement the 2 pi pairs when you don't know the value of the signal. And that's all like, the signal processing, like, or like adiabatic procedure. That's one thing. But the same story with the frequency. What if it's not perfectly resonant, but slightly off resonant? And also the value is not known. So how do you robustly engineer like 2 pi pairs? So that's exactly, the composite pulse idea, and that's where the signal processing comes into play. Yes.
Yeah, okay. So I came in a few minutes late, and forgive me if you answered this in the beginning. I have 2 related questions. It's about sensitivity to errors and error correction. And if you're basically combining the sensing and the computing, you feel like, repeated C naughts or, gates that are doing the processing. I think to do that, at large scale, you would need to do some kind of fault tolerant approach. And two questions is how sensitive are is the algorithm that you developed to errors? And the second question is it obvious how to go from, like, a qubit is sensitive to a field in a certain way that you understand, but is it obvious how to get that mapped into a logical qubit? Because, like, logical qubits as implemented are usually insensitive to a lot of things. That's what makes them great.
Exactly. So I think the second question is this. So we literally need to understand that better. So what is the fundamental limit of interfacing noisy sensors to logical degrees of freedom? Okay, there are some works in certain cases, basically based on, okay, what is a quantum sensing and error correction and their compatibility. Turns out their analysis is relying on evaluating the scaling of quantum Fisher information. But what our algorithm tells us is quantum Fisher information is not a good figure of merit because it goes to zero in optimal case. And then any Fisher information-based algorithm cannot achieve optimality. So we need to have more, better, non-perturbative, more digitized approach of understanding the interface. So I'm not answering your question because I don't know. I'm just reiterating that's an important research direction. The first one is how it's robust against, say, implementation of gate error and so on. It is quite sensitive, just like the Grover's algorithm is sensitive. Grover algorithm, even though the number of register qubit is small, the iteration is exponential in the size of the iterations. So if you have a single error, that will accumulate over a long time. So we need to make sure the amount of error is exponentially small compared to the size of the computer. At least the version that we know of for now. Yeah. Yes. Yeah, Nico?
The idea of coupling to a sensor to a quantum computer seems fairly rich new perspective. You pointed out that there are some metrological problems which we don't want to apply this approach, maybe because of the role of quantum Fisher information. But since there's still very many problems within quantum metrology, do you see other ones as essentially being able to benefit from your approach of looking at the quantum computer?
I don't know. So I think I totally get a wide open direction. So what I tell my friends and colleagues are that let's look away from just optimizing sensitivity to one parameters. Let's consider time-dependent signals, multi-parameter signals, estimating the functions of the multiple parameters as studied here. Maybe not the sensitivity as a figure of merit, pattern matching. So for example, LIGO's experiment is not just detecting in the signals, but it's finding a particular pattern of the signal, right? That sounds very much like where the computer science can kick in, but I'm not very expert on that, right? So I think that direction is very interesting direction. Just that, it's just sensing, but go away from necessarily sensitivity improvement. That's right. Yeah.
One last question.
So I might have missed it, but compare the conventional AC sensing time and I remember there was N. Is it the number of sensors?
Yeah, that's the number of sensors.
Sensing it takes less advantage of having more sensors.
Oh no, it's better to have more sensors. So where is it? Yeah, so here. So we want to minimize how? Oh, that's not the case because we need to do the comparison carefully. So maybe you are saying here, scaling of n is 1 over n to the power 3/2. Here, the scaling is 1 over n squared, right? But let's assume we are fixing B mean and delta omega. But that's not the figure of merit. When you do is that the figure of merit? So suppose we fix delta omega and then B mean. Oh, yeah, sorry, okay. So suppose delta omega and B mean is fixed, But here we have a square root, but here we don't have a square root. So they should be fixed and should be order 1, so that the square root doesn't change them. Okay. In that case, we don't have any improvement because it's not a broadband sensing. Okay, good.
Okay. Well, that's one again.
Thank you.